Okay, so example number three now we've got an explosion, and this is a pretty typical conservation of momentum type of question, where you've got a bullet being fired from a gun. So we've got a bullet of mass 4 grams fired from a rifle that has a mass 2 kilograms. I'm going to label that. I'm going to highlight that in a different color. They say, so the bullet of mass 4 grams is fired from a rifle of mass 2 kilograms with a muzzle velocity. The muzzle of the gun is basically the barrel of the gun. So the top part of the barrel is called the muzzle. The muzzle velocity is 380 meters per second. And then, confusingly enough, what they ask for here is what is the initial recoil velocity of the rifle? Well, the fact that they use the word initial, you might think, well, that's the initial speed, but it's not. It's actually the final speed of the rifle after the explosion. So just be careful of that word initial. What they mean there is, initially it's going to kick back with a certain speed, but because it's probably up against somebody's shoulder, when it does that, chances are that velocity is going to decrease pretty quickly. That's usually what happens in a real world situation. Okay, so we've got our data listed. Now I'm just going to make a proper list. I've got mass. I'm going to use B for the bullet. The mass of the bullet is 4 grams, 4.0 grams, which is 4.0. Well, I'm actually not going to use scientific notation on this because I don't want to complicate things as much as I can. So that's 0.004 kilograms. They actually give us that in the question. We know that the velocity of the bullet, the initial velocity of the bullet U is, actually, we know that the initial velocity of the bullet U is going to be 0, because before the gun is fired, it's obviously not moving. The bullet is not moving. You can see it right here at the top of in the picture if you look closely. So that bullet's not moving at all. We also know that the mass of the gun, I'm going to use G for the gun, is 2.0 kilograms. And again, the initial velocity of the gun is also going to be 0. Okay, so we've got our information, or most of it. We know that all of this is before. Notice I actually didn't draw a picture here, well, because they gave us a picture. After the collision, or after the explosion, I should say, we want to be able to figure out what's the final velocity of this one here. So again, the mass of the bullet has not changed. That's 0.004 kilograms. We do know that its velocity has changed. That is now 380 meters per second, and it's going to the right. Okay, so at this point we start actually talking about something called a frame of reference. So if something's going to the right, or if anything is pointing to the right, because velocity is a vector quantity, we give that a positive sign. And if anything is going to be moving to the left or pointing to the left, then we give that a negative sign. Just think about your number line, okay? All the positive numbers are on the right hand side, all the negative numbers are on the left hand side. So after the explosion, we would have the mass of the gun, again, has not changed. That is 2.0 kilograms. And we're looking for the final velocity of the gun. Okay, that's what we're after. Now, if you notice, nothing is moving before the explosion. And this is a pretty common example, okay? So that means that the total momentum on the left has to be 0, but let's make sure that the math gives us that, okay? So the momentum before, mass of the bullet, times the initial velocity of the bullet, plus the mass of the gun, times the initial velocity of the gun, is going to be equal to mass of the bullet times the final velocity of the bullet plus the mass of the gun times the final velocity of the gun. I know that's a bit of a mouthful of an equation, but about half of that is just about to disappear in a second. So I know that this one is 0.004. I'll plug in the numbers. The initial speed of the bullet is 0 plus 2.0 kilograms for the gun times 0 meters per second equal to the mass of the bullet 0.004. We know that the final velocity or the muzzle velocity of the bullet is 380 meters per second. Plus the mass of the gun, which is 2.0 kilograms, times that final velocity of the gun. Now, because the bullet is going to be moving to the right, like we said, that's going to have a positive sign. So we should be expecting that the gun will be moving to the left or in the negative direction. Okay. So notice that we've got zeros multiplying these two quantities. So they are both gone. On the left-hand side, I've got 0 completely. On the right-hand side, I've got 1.52 kilogram meters seconds to minus 1, and that's the momentum of the bullet afterwards. And of course, that's a positive momentum because it's moving to the right. Plus 2 times the mass of the 2 kilograms times the velocity of the gun. So a little bit of algebra here. What we do is we subtract 1.52 from both sides. So that one will cancel out that one, and that leaves me with negative 1.52 kilogram meters seconds to minus 1 equal to twice the final velocity of the gun. Last little step is to divide both sides by 2. That's 2 kgs that I'm going to be dividing it by, because that was 2 kgs on top. So that one cancels there. Here I've got 2 into that quantity there, but watch the unit. The kilogram cancels with the kilogram, and I'm going to be left with a unit of meters per second. Meters per second. So that gives the final velocity of the gun equal to negative 0.76 meters per second. So the negative just means it's moving to the left, that's all. So let me just again look at this in terms of vectors. Initially, there was, I'll come back to the picture again for a second. So initially there was no momentum at all. So before the explosion, momentum here was 0. Which means that after the collision, after the explosion, I need to have a 0 momentum as well. Okay. Now you can see that the bullet is not going to have a 0 momentum by itself. That's going to be going this way. So this won't be the momentum of the bullet after the collision, after the explosion, sorry. But the system is made up of 2 particles, the bullet and the gun, okay? And we said that it's the total momentum that's conserved, not just the momentum of any one of them, the total momentum. So the momentum of the bullet is this much, we'll say, to the right. Then the momentum of the gun has to be this much to the left. That way, the momentum of the gun cancels out the momentum of the bullet. So the net effect is that the total momentum after the explosion is also zero. Okay? So I hope that makes some sense. Again, just to recap, total momentum before the explosion, zero. Total momentum after the explosion must also be zero. Remember that there's two particles in that system. So whatever the momentum is for one of them has to be cancelled out by the momentum for the other one. Okay, so I know it's been a long one, but I do think it's an important example because, like I said, it's a pretty common problem when it comes to momentum. Okay, thank you.